Deep beneath the Earth's surface lies a realm of molten rock known as magma. Volcanic eruptions occur when this fiery concoction forces its way up through the Earth's crust. The result is a spectacular release of molten rock, gas, and ash, often with devastating consequences. These events have shaped our planet for millennia, leaving behind a trail of destruction and creation in equal measure. Volcanic eruptions are a powerful reminder of the immense forces at work within our planet. They are a testament to the Earth's dynamic nature, constantly evolving and reshaping itself over time. Understanding the causes and consequences of these eruptions is crucial for mitigating their potential impact on human populations and the environment. Volcanoes are not random occurrences. They are most often found where tectonic plates, the massive slabs that make up the Earth's crust, either collide or move apart. These zones of intense geological activity provide pathways for magma to rise from the Earth's interior. In conclusion, volcanic eruptions are a complex and awe-inspiring phenomenon. They are a testament to the power of nature and a reminder of our planet's constant state of flux. By understanding the science behind these events, we can better prepare for their hazards and appreciate their role in shaping the world around us. The generation of magma is the first step in the process of a volcanic eruption. Deep within the Earth's mantle, temperatures and pressures are extreme. These conditions can cause solid rock to melt, forming magma. This process is influenced by several factors, including the composition of the rock, the presence of water, and the amount of heat available. One of the primary mechanisms of magma generation is the upward movement of mantle plumes. These plumes are columns of hot, buoyant rock that rise from the Earth's mantle. As they ascend, they encounter lower pressures, which causes them to melt partially. This molten material, being less dense than the surrounding solid rock, continues to rise toward the surface. Another significant contributor to magma generation is the process of subduction. At convergent plate boundaries, where tectonic plates collide, one plate is forced beneath the other into the mantle. The descending plate, subjected to increasing temperatures and pressures, releases water and other volatile compounds. These volatiles lower the melting point of the surrounding mantle rock, leading to the formation of magma. In addition to mantle plumes and subduction zones, magma can also form at rift zones. These are areas where tectonic plates are moving apart, creating space for magma to rise from the mantle. As the plates diverge, the pressure on the underlying mantle decreases, causing it to melt and generate magma. This process is responsible for the formation of mid-ocean ridges, vast underwater mountain ranges formed by the upwelling of magma at divergent plate boundaries. Understanding the mechanisms of magma generation is crucial for predicting volcanic eruptions and mitigating their potential hazards. By studying the composition of magma and the geological context in which it forms, scientists can gain insights into the processes occurring deep within the Earth and assess the likelihood of future eruptions. Once magma forms, its journey to the surface is a complex and fascinating process. Driven by buoyancy, the molten rock, being less dense than the surrounding solid rock, begins its ascent through the Earth's crust. This journey is not a simple upward flow. Rather, it is a treacherous path fraught with obstacles and diversions. The ascent of magma is primarily governed by the difference in density between the magma and the surrounding rocks. The greater the density contrast, the stronger the buoyant force pushing the magma upward. However, the viscosity of the magma, a measure of its resistance to flow, also plays a crucial role. Highly viscous magmas, like those rich in silica, tend to move more slowly and are more likely to get trapped within the crust. The Earth's crust is not a uniform, solid mass. Instead, it is riddled with cracks, fissures, and faults. These discontinuities in the crust provide pathways for magma to ascend. The magma exploits these pre-existing weaknesses to force its way upward, often widening them in the process. As the magma ascends, the pressure on it decreases. This decrease in pressure can cause dissolved gases within the magma to come out of solution, forming bubbles. This process, known as vesiculation, can significantly increase the volume of the magma and accelerate its ascent. The presence of these gas bubbles also plays a critical role in determining the type of volcanic eruption. The journey of magma from its source to the Earth's surface is a complex interplay of buoyancy, viscosity, and the structural properties of the Earth's crust. Understanding this journey is crucial for forecasting volcanic eruptions and mitigating their potential hazards. The rate of ascent, the amount of gas within the magma, and the pathways it takes all influence the style and magnitude of the eruption that ultimately unfolds. All right, let's dive into the fascinating world of volcanic eruptions. You see, not all eruptions are the same. They vary in scale, intensity, and impact. Now, there are several types of volcanic eruptions, each with its own unique characteristics. The most common types are Hawaiian, Strombolian, Volcanian, and Plinian. Hawaiian eruptions are typically gentle and produce flowing lava fountains. Strombolian eruptions are more explosive, with bursts of lava and gas. Volcanian eruptions are even more violent, ejecting ash bombs and blocks. And then we have Plinian eruptions, which are the most powerful, sending massive columns of gas and volcanic debris high into the stratosphere. Understanding these different types helps us better predict and prepare for volcanic activity. It's truly remarkable how diverse and dynamic our planet can be. Volcanic eruptions can be incredibly destructive, and they pose numerous hazards to both people and the environment. From lava flows that incinerate everything in their path to ash clouds that can disrupt air travel and cause respiratory problems, the dangers are multifaceted. Furthermore, volcanic gases such as sulfur dioxide can lead to acid rain and have long-term impacts on climate. Understanding these hazards is crucial for preparing and protecting communities living in the shadow of these powerful natural phenomena. Monitoring volcanic activity is essential for early warning and risk mitigation. Scientists employ a variety of techniques to keep an eye on volcanoes. Seismographs detect earthquakes that often precede eruptions, while satellite imagery helps track changes in the landscape. Gas emissions are measured to gauge the likelihood of an eruption, and ground deformation is monitored using GPS technology. By combining these methods, experts can provide timely alerts and hopefully reduce the impact of volcanic events on human lives. Throughout history, there have been several volcanic eruptions that have left an indelible mark. The eruption of Mount Vesuvius in 79 AD buried the cities of Pompeii and Herculaneum, preserving them for centuries. The eruption of Krakatoa in 1883 was so powerful that it altered global weather patterns and produced stunning sunsets worldwide. More recently, the eruption of Mount St. Helens in 1980 was a stark reminder of the destructive power of volcanoes, reshaping the landscape and providing valuable scientific insights. While volcanic eruptions can be destructive, they also bring numerous benefits. Volcanic soil is incredibly fertile, supporting lush vegetation and agriculture in many regions. Volcanic activity also creates stunning landscapes, attracting tourists and boosting local economies. Additionally, geothermal energy harnessed from volcanic heat provides a sustainable and renewable energy source. So, in many ways, volcanoes contribute to the richness and diversity of life on Earth.